Hello, and welcome to the second video in the Sienna Data training series. I am Kate Doubleday, and today's video will focus a little bit on how Sienna Data works. So Sienna is an open source ecosystem of scalable power system modeling and analysis capabilities in the Julia programming language. It has three core capabilities, each enabled by a set of Julia packages. Sienna Data enables efficient data input, analysis, and transformation. Sienna Ops enables systems scheduling simulations by formulating and solving optimization problems like unit commitment, economic dispatch, and optimal power flow, and enables sequential simulations for production cost modeling. Sienna Dyne enables system transient analysis, including small signal stability and full system dynamic simulations suitable to represent electromagnetic transients. So today, we'll focus on how Sienna Data works. Sienna Data is a combination of 5 different Julia packages, with powersystems.jl being the focus. But before we get into each of these 5 packages, we'll talk a little bit about Sienna's approach to modeling data. Within Sienna, we separate data and equations. So the idea is that if you are trying to represent a wind generator, the equations you would use to represent its behavior in a unit commitment simulation are very different than in a small signal stability analysis. So we can separate the basic data that doesn't change, like that wind generator's capacity and its location, and any other input data we might need, from the equations that we use to describe its behavior in a particular problem. So in Sienna, we call these data models types, and the operational models that describe behavior formulations. So for the different components within a system, the generators, loads, services, and network topology, there are well-defined types that describe those groups of components consistently throughout the simulations. Those data models can be populated with input data from CSV files of time series or other types of files such as PSSE or MatPower files. And that is all separate from defining the particular equations we would use to describe behavior in a certain problem. Of course, within Sienna, in the next stage, you can combine both data and equations to describe a particular problem, like an optimization problem or stability analysis, and then solve it. For today's focus, we're really looking at the top part of the structure. So the data types separate from the formulations that describe behavior. Within Sienna Data, we have parsers that populate these data models with the input data, some preliminary data manipulation functions, and we also have available some visualizations to take a look at input time series, for example. So that's all separate from what's going on in Sienna Ops and Sienna Dyne to describe the formulation of behavior of a component in a particular problem. That will be covered in future videos. So within Sienna Data, we have these 5 Julia packages. And the powerhouse is, again, powersystems.jl. And this is the set of functions we use to parse and format input data for consistent representation of various components of a similar type. So for example, all wind generators are represented consistently. Power Graphics allows you to visualize some of those data inputs. Power network matrices can be used to build common matrices such as the YBus, PTDF, and LODF matrices. Power System Case Builder is a useful utility to load either existing test system data or your own custom test system data. And it comes available with some data you can use for preliminary exploration before you've built your own custom system. Powerflows.jl can be used to calculate some simple power flows outside of something like a sequential production cost modeling problem. So let's talk a little bit more about the type hierarchy. Within Sienna Data, the main container that describes a power system is called a system, and it includes some basic information about the whole system, while also being a container for the various devices and services within the system. So within that set of components, we have these well-defined types that describe different types of generator, static injections, different types of loads, services, and the topology. Each of those types has a well-defined set of input data required to model a component of that type. And time series data can be attached to any device parameter. So there's a lot of flexibility there. So let's look at some examples. I'm going to switch to a code demonstration. So I'm starting by loading in 2 of the 5 packages within Sienna Data, Power Systems version 3.0.1, and Power Systems Case Builder 1.2.1, as well as Type Tree, which is just a utility that's not part of Sienna. So the first thing we'll do is explore the type library, the model library that we were just looking at. So this is the type hierarchy of these well-defined data types available within Sienna. So that includes, again, dynamic device parameters, our different branches, loads, generators, and time series data. So it's important to note that this is not a one-way hierarchy. Different components can have cross-references across this type hierarchy. So for example, you might have a load that has a time series data attached to one of its parameters that's describing how that load varies over time. We'll also take a look further into the dynamic component library in videos on Sienna Dyne. So let's take a look at, again, that main overall structure, the system. So I'm using the help function here to take a look at the system function. So this describes the various different ways that you can define a system using Julia's multiple dispatch, as well as the main inputs, which include some overall description of the system's base power for unitization, the components within the system, and the time series data attached to those components. If I look at a specific example, I can load in a system using Power System Case Builder. We see, first of all, the general information about the system, including that base power of 100 megawatts. This is also a 60 hertz system, and it has 35 components. We also see some general information about those components. So those 35 components include various different types, describing the topology, the generation, including a bunch of hydro in the system, and the loads. We can also see which of those components are time varying. So some of them have time series data attached, and that also includes, in some cases, some forecasts as well as realizations. We also see some general information about that time series data. So we have 6 components in this system with time series, and we can also see some general information about the resolution that we're looking at and the date range available. So we've got 3 months of hourly resolution data, including both forecasts and realizations. Okay, so if we want to investigate any more into the various data types for individual components in this in Sienna Data, we can always use the help function to see more about the structure of the data type and what can be represented and what's required in order to represent a component of this type. In this case, we're looking at a hydro generator, and specifically a hydro generator with a reservoir. If you are interested in more information and more exploration about Sienna Data's data types, I'd encourage you to go to the powersystems.jl documentation, which includes 3 sections that are useful when you're getting started. The tutorial section has a bunch of example code. The modeler guide is also very helpful for understanding more about the type structure and what type of data can be represented. The next two sections are a little more advanced, but if you come down to the model library at the end here, you can also see, again, that same information that's in the help function for each of the data types. So you can explore what's available to represent, for example, dispatchable hydro generators, and what that data structure looks like. So I'll go ahead and leave it there for now, but we'll look forward to seeing you in the next videos on Sienna Ops and Sienna Dyn. So thank you very much.